Okay, so back to our video. We just finished the resource page. So we know what a rational and irrational number are now. We know the difference between integer, whole, and natural, and we know how to classify them all now. Now that we know all of that, we want to apply it to our lesson within our book. How we're going to get to our book is we're going to go to clever.com. If you haven't been to it yet, this is your single sign-on portal for everything we're going to do. You can get to Schoology from there. You can get to Pearson, which is our textbook. You can get to everything. You're going to click log in as a student over here in the right top corner. And then it's going to ask you to type in the school. So type in South Haven High School, and then it's going to ask for your lunch number. I've already logged in with my number, so it's going to take me to my page. Yours is going to look a little different because you're not going to have the teacher side of it, but you're going to have all of these apps down here. What we want to go to for our book is the 6 through 12 Pearson Savvas textbook. There's another app down here that says Pearson Easy Bridge. This link does not always work, so don't go there. You want to go to the Pearson Savvas with the little textbook icon. Once you get into there, it's going to ask you to sign on. You're going to sign on using your lunch number, again, for your username and your password. And then it's going to show you your courses. You're only going to have one course here. I have 3 because I have 3 blocks. But you're going to click on your book. And then you'll be able to see your book right here. This is our textbook. This is where you'll see all of your class assignments that I assign. And then any test scores, any practice scores, anything that you do within the class. Once you open your book, you won't see the teacher edition, but you'll see the interactive student edition. Sometimes this takes a minute to load, so I already loaded it beforehand. And you'll see the regular book out here. So yeah, this will take a minute. So you'll see all the topics we're going to cover this year. You can click on any of them, but we're going to stick with topic 1. We're going to solve equations and inequalities. We're not solving equations today, but we will get there. Today, we just have to learn the basics about rational and irrational before we get to solving equations. So you'll see the textbook exactly how it is for the physical copy. And it'll also have some interactive stuff in there if you just keep clicking next. We're going to go to example 1. So keep clicking next until you get to example 1. And I'm going to do it on my teacher side so that I can see everything that I need to see to be able to do this for you. So, but it looks exactly the same within your book. So you have the same exact question right here. So the very first question for example 1 says, in the set of numbers from 1 to 10, which elements are in both the subset of even numbers and the subset of multiples? When you're talking about a set of numbers, this is literally just a list of numbers that you have that are put together in a group. We group them with braces, and braces are just little squiggly lines. They're kind of like parentheses, but they get a little curve to them and a little squiggle on the end. And then we just make a list of numbers in there, like 1, 2, 3, 4. That's a set of numbers. For this example, we want a set of numbers from 1 to 10. So I'm going to expand this just a little bit. So we want to go all the way to 10. And then we want to know which elements. Elements just means which numbers. Which numbers would be both in a subset of even numbers. A subset just means we're talking about another set. So I'm going to call this set A. And then I'm going to give us another set, and I'm going to call it B. What would be in a subset of even numbers? So for even numbers, which ones out of here are even? Well, you have 2, 4, 6, 8, and 10. So out of that top set of numbers, we have a subset of just even. And then when they want another subset of just multiples of 5. Multiples of 5 means that your number multiplies by 5 to get it. So nothing multiplies by 5 to give you 1 or 2 or 3 or 4. But 5 times 1 is 5. Nothing gives you 6, 7, 8, 9. But 5 times 2 gives you 10. These are just numbers that can multiply with 5 to give you those numbers. So these are multiples of 5. So we have our main set of 1 to 10. We have our subset of even numbers. And we have our subset of multiples of 5. So of that, which numbers are in both of our subsets? So these two right here. If we look at our subsets, we just need to see what do they have in common. Do they have a 2 in common, a 4, a 6, an 8, a 10, or a 5? Well, the only number we see that they have in common is 10. So 10 would be our element in both. And you can do this on your side too. You can always check your solution. And like I said, this gives you the notes that I just told you about, that your set it says a collection of objects. We use numbers. We don't use other objects. And it's just a list of those elements. So you have your set 1 through 10, like we did up here. You have your subset of even numbers, 2, 4, 6, 8, 10. And then your subset of multiples of 5, 5 and 10. And the only number they have in common that's in both of them is 10. Okay, on the next page of your book, you're going to have a try it. Sorry, that's in your workbook. So if you go to your workbook on lesson 1, the first thing you're going to see is a try it. Let me pull that one up. It says try it, and then it says which numbers in set A, still 1 through 10, are elements in both subsets of odd numbers and the subset of multiples of 3. So we have our main set, 1 through 10, but we need another subset. So I'm going to call the first one B. And what are your odd numbers within this list? Well, it's the opposite of what we did earlier. You have 1, 3, 5, 7, 9. Those are your odd. And then we want a subset that has multiples of 3. What multiplies by 3? So 1 times nothing, or nothing times 3 gives us 1. Nothing times 3 gives us 2. But 3 times 1 gives us 3. And if you keep going down your list, you'll get to 6, because 3 times 2 is 6. And then 3 times 3 is 9. And 3 times 4 is 12, and that's not on our list, so that covers all of them. Those are going to be your multiples of 3. So then which numbers are in both? Do they have a 1 in common, a 3 in common? Well, we see 3 right here. Do they have a 5, a 7, a 9? We see our 9s. And then that one didn't have a 6. So for this, we're going to have 3 and 9. Then you can check it. So in set A, 3 and 9 are in both the subset of odd numbers and the subset of multiples of 3. So we did it. Okay, I have one more example. This is not in your book. I just want to touch base with it and make sure you got it. So one more example. You can write this in the margin of your workbook. Given this set of numbers, this set right here, 5, 6, 7, 8, 9, 10, 11, 12, which numbers are both in the subset of numbers divisible by 2 and divisible by 3? So for divisible by 2, we want to look at which of these numbers divide by 2. 5 divided by, and give us a whole number. We're not looking at fractions here. So 5 divided by 2 is a decimal. 6 divided by 2 is 3, so that's one of them. 7 divided by 2 is a decimal. 8 divided by 2 is 4, so that's one of them. 9 divided by 2 is a decimal. 10 divided by 2 is 5. 11 divided by 2 is a decimal, but 12 divided by 2 is 6. So when you're looking at numbers divisible by 2, you're going to look at your even numbers pretty much. Not pretty much, exactly. So these are divisible by 2. Then I'm going to grab another subset, and we want numbers divisible by 3. Which of these numbers divide by 3? I'm not going to go down the full list again like I did before, but this one kind of goes with the last problem we did. 6 divided by 3 gave us 2, so that's divisible by 3. 9 divided by 3 is 3, so that one works. And 12 divided by 3 is 3, so that one works as well. Sorry, 12 divided by 3 is 4. So those are your numbers divisible by 3. So which numbers are in both of them? So if you go down your list, do they both have a 6? Yes. Do they both have an 8? No. A 10? No. A 12? And then this one has a 9, but the top didn't. So we're just looking at 6 and 12. And then we'll check our solution. So like I said, just like I did, they have their top list. They made a list divisible by 2, a list divisible by 3, and then 6 and 12 were the only numbers that they had in common. Okay, on to example 2. Example 2, we're going to compare our real numbers, our rational numbers, and irrational numbers. So, for example 2, this comes straight out of your book. Jim is playing a math game where he needs to put a set of 3 cards in numerical order, and these are his cards he's shown, and we need to order them from least to greatest. We're not going to make you simplify fractions or do anything like that. The easiest way you can do this is to plug them into your calculator. So, let me get rid of this big old screen. So our first one, it's easier to compare them if they're decimals. So I'm going to put, instead of putting this in as a fraction, I'm just going to put 40 divided by 11. That's all a fraction is. A fraction is just division. So 40 divided by 11 is 3.6363 repeating. Then this square root. To get a square root, if you haven't done the calculator scavenger hunt, you're going to do second x squared, which is over here on the left in the middle. And then again, I'm not going to plug this in as a fraction because we want a decimal to compare it. So we have 324 divided by 36. That one gave us 3. And then the last one, square root of 10. So again, second x squared, and plug in your 10. So we have 3.63 repeating, 3, and 3.16 with a long decimal. So, trying to get over it. 3.63 repeating, 3, and I'm going to round this off to the last one off to 3.16. So, least to greatest, which one is the lowest? We look at our decimals. They all start with 3, so that doesn't help us. But this one right here, it's not a decimal, but it does have a number after it. If there's nothing there, it's going to be 0. So look at your first decimal place. We have 6, we have 0, and we have 1. Which one's the least? Well, 0. So that's going to go first. Which one's next? That's going to be your 1, so 3.16. And then the highest decimal place there is 63, so 3.63. But we need to make sure we grab the numbers they gave us originally. Remember, the first one we did was 40 over 11, so that's actually the greatest number on our list. The second one was that square root of 324 over 36, and that actually came first in our least to greatest list. And then that 3.16 came from square root of 10, and that ended up being in the middle. So this is your least to greatest order, and we can check it. And they put it on a number line here. It didn't ask us to put it on a number line, so I didn't. But this is what it would look like if you did put it on a number line. So square root of 324 over 36 ended up being just a plain old 3, so it would go on 3. Square root of 10 was a little more than 3 1/2. Sorry, wrong one. Was a little more than 3, so it goes just slightly after it. 40 over 11 was a little more than 3 1/2, so it goes a little bit after 3 1/2. And then just listing them out least to greatest exactly like we had it. Okay, and then the try it is in your workbook. So go to the example 2, try it in your workbook, and we're going to list these from least to greatest. So this one's already a decimal, we don't have to worry about that, but we need to change the rest of them to decimals. So the first one we have is square root of 1 over 9. So second x squared gives you a square root. And I want a decimal, so I'm just going to put 1 divided by 9 to get a decimal. So that's 0.333. I'm just going to write it over it. And then 6 over 25, we're just going to put 6 divided by 25. And that one's 0.24. So, which one of those is the least? We got 0.25 cents, 30 cents, or 24 cents. Well, 24 cents is going to be the least. So I'm going to type it in as a decimal and see what it gives me, because it doesn't give us a square root option. So I'm going to put 0.24 first, and then 25 cents is next. And last would be our 0.3 repeating, which would be 33 cents if you kept repeating it. And that's exactly what it gave us. That 0.24 was 6 over 25, and that came first, which we did. 0.25 came second, and then that square root came last. And that's what you got here. Okay, so I'd like y'all to pause the video and try this one by yourself before we move on. See if you can get it, and then we'll come back and check it. Okay, so hopefully you paused the video and tried it by yourself. Let's see, let's check it. So the first one, let's change it to decimals. We have square root of 121 over 25. That's 2.2. And the next one is 2.25. That's already a decimal. And the last one is square root of 5. And that'll give us 2.24 if we round it correctly. So these numbers are all super, super close together. So we need to figure out which one goes first. So since these already have 2 decimal places, I'm going to add a second one to this to make sure everyone can see what we're doing. If you don't have a number, just add a 0 at the end. So which one comes first? $2.20, $2.25, or $2.24? Well, $2.20 is the cheapest. Then you got $2.24. Then you have $2.25. So it's going to be the square root of 121 over 25, then the square root of 5, and last the decimal 2.25. See if we get it right. Square root of 121 over 5, which was 220, square root of 5, which was 224, and 2.25. Perfect. Okay, let's move on to example 3. Okay, this one is the sum of two rational numbers always rational? Well, if we go back to the list that we made on the resource page, which I showed down here, we know that rational numbers are fractions and decimals that end or repeat. So we have 2 over 3 as a fraction, 0.4 repeating as a fraction, as a repeating decimal, and 6.7 as a decimal that ends. Underneath that category, we also have integers, whole numbers, and naturals. These are all going to be rational numbers, everything on this side. So, when we're looking at the sum of two rational numbers, sum means we're going to be adding. So we're going to take a rational number, which is a fraction or repeating decimal or ending decimal. Repeating decimals and ending decimals, they can always be turned into fractions if you put them in your calculator. So we're going to stick with fractions. I'm going to call it just A over B because we don't have numbers. And then two rational numbers. So we want to get 2 of them. So I'm going to do C over D. And we want to see if that still comes out to a fraction. I'm not going to write that there. So if you remember, I'm going to plug in random numbers real quick. If we're adding fractions up, we have to find that common denominator and then multiply it by the top. So like 3 times 7 would give us 21 on the bottom. And then you have to multiply it by the top. So 3 times 7 is 21, so we have to do that to the top as well to get 14. 7 times 3 gives us 21, so we have to do it to the top as well to get 18. That's the same thing we're going to do here. So we have our B and D. Because they're letters, you can't really get a single number for that, so our common denominator is just going to be B and D. So what did we add to B to get BD? Well, we didn't add, we multiplied by D. So we're going to do that on top as well, which gives us AD. Same thing over here. To get BD, you have to multiply by B. Same thing on the top. So we're going to have BC. Now, you can combine them up if you want to. If you want to have one big fraction, like down here, if we wanted one big fraction, we could just put it over 21, and we would get 32 on top. You can do the same thing here. If you just want one fraction, you could just combine the top. So we have AD on the first one plus BC. But how does that help us determine if that rational still stayed irrational with all of these letters? When we're looking at rationals rational numbers, we always want to look at it in terms of fractions, but also within that fraction, we want to look at it as integers. Just like these down here. 2 is an integer, 3 is an integer, 6 is an integer, 7 is an integer. When we change the denominator, 21, that 3 times 7, 21 is still an integer on both of them. When we had to multiply to get the top number, 14 and 18 still stayed integers. Even when we added it all together, we still had 32 on top, which is an integer, and 21 on the bottom, which is an integer. And if we go back to our rational, irrational chart, where do integers fall? Do they fall on the rational side or the irrational side? Well, they're right here on our rational side. So if your fraction that you're using is filled with integers and say like not square root of 2 over 7 or anything that's irrational like pi, you put like pi over square root of 5, these are irrational numbers. As long as it's filled with integers or rational numbers, it's always going to stay rational. If you add a rational plus a rational, it's going to stay rational. Just like if you add, take material objects for instance. If you add a pencil and bring in another pencil, you don't just magically have markers. You still have pencils. So they're always going to stay the same. So it doesn't matter what the numbers are. You could put any numbers into this box. If you add a rational plus a rational number, it always stays rational. Now, the only reason I went through these letters with you is because when you see your solution in your book, it's going to have those letters if you keep going. They gave you random numbers to look at first, but the main thing to know is as long as your numbers are integers, it doesn't matter what numbers you add together. They're always going to stay integers. Now, the last little thing I want to talk about on this, it says that B can't be 0 and D can't be 0. That's because you cannot divide by 0. You can check it out in your calculator. If you check it out in your calculator and you put like 7 divided by 0, it's going to give you an error. We can't divide by 0. That's not a math calculation because you can't divide into nothing. You can divide in by like a pizza. You can divide it into one person or two people or three people, but you can't divide it into no people. So, but the main part of this is as long as your numbers are rational, they're going to stay rational. Just like if you add a pencil plus a pencil, you still have a pencil. It doesn't change to a marker. Okay, so let's look at B. So is the product of a rational times a rational always rational? Product means multiplication. So if I take those same fractions, you can do the letters if you want to do the letters. Or if you want to stick with numbers, you can do that. But again, rationals are going to be your fractions. Within those fractions, it has to be an integer, just a regular everyday number, like 4 and 5. And let's go 8 and 3. So if we take these, they're all integers no matter what, because it's rational, and we multiply them together. What do we get? Well, on the letter side of this, you can multiply it together, and you just multiply straight across. What's A times C? That just gives you AC. For B times D, it's just going to give you BD. They're still integers, but it's kind of confusing. So I like to plug in numbers like I did on the last example. If we take 4 times 8, what do we get? Well, we get 32. If we take 5 times 3, what do we get? 15. Are your numbers still integers? Yes. As long as they stay integers, it's always going to be rational. And just like on the last one, you don't want to put as your fraction like 4 over 0. 0 is an integer, but we can't divide by it. So it can't be at the bottom of a fraction. It has to be numbers other than 0. So, and you can check your solution. Again, because it's always going to stay integers, it's always going to be rational. So let's check it. They did the letters, A over B times C over D. They're all integers, so you're still going to get integers in your answer. If that's really confusing, so if you just want to plug in numbers for these and see if your numbers still come out to integers, that's what I would recommend doing. Okay, and then I got one more. So to try it, this is going to be in your workbook. In your workbook, you can take your notes for this one. Is the quotient of two rational numbers always a rational number? So if we take our fractions, I'm not going to go the A, B, C, D. I'm going to use regular numbers. Again, we still have fractions because they're rational, but within our fractions, we need to have integers. No square roots, no weird decimals, nothing like that. They need to be integers. So I'm going to use, let's go 4 and 5 again, and 2 and 3. If we divide this, do we still keep our integers, which make it rational? Well, when you're dividing, you keep, flip, and change. So we're going to keep our first fraction. We're going to flip our second fraction upside down. And we're going to change our sign to multiplication. And then we just multiply across. So 4 times 3 is 12. 5 times 2 is 10. You can reduce this. You can do it in your calculator or do it by hand. They both go into 2. So if you want to divide by 2, or they both divide by 2. They don't go into 2. 12 divided by 2 is 6. 10 divided by 2 is 5. So when we solve it out, when we divide it, do we still get integers? Is 6 an integer? Is 5 an integer? Remember, integers are your numbers that have no decimals. They can be positive or negative, but they're not going to have any decimals on them. Well, 6 doesn't have a decimal. 5 doesn't have a decimal, which means they are integers. So because they're both integers on the top and the bottom, it's going to be rational. So is the quotient of two rational numbers always rational? Yes. And your explanation, that would be your explanation. I can't type all of that into the box, but this would be your explanation. Of course, they use the numbers again, which is completely fine. A over B times C over D. The letters get super confusing, so you can plug in numbers and check it out like I did. Okay, example 4. Now we're going to work with rational and irrational. I am not going to watch the video on these. Y'all are more than welcome to go watch the video, but it gets really confusing. They don't use numbers at all. They strictly use the letters, and that's all they talk about. I'm going to have y'all plug in numbers to use for this because it's going to make a lot more sense. So, if we take the sum of a rational number and an irrational, will your answer be rational or irrational? This is no longer pencils plus pencils equals pencils. This is pencils plus markers equals what? What do we get if we add pencils and markers? So again, sum means add. Rational, if we go back to our chart, that is our fractions. So you want a fraction. I'm going to stick with A over B for a second, but I will put numbers in there. Irrational, I'm going to go back to the chart for that one because we haven't looked at it yet. Irrational are your decimals that never end or repeat. So 4.8325215 ... Pi is an irrational because it's 3.1415 ... And square roots that we don't know, like square root of 2. So any of those are irrational. So pi and square root of 2, or really long decimals that don't repeat and don't end. So if we take a rational, which would be a fraction, I'm just going to plug in a random number for that, like 2 over 3. That's our rational number. If we add an irrational, you can pick any number from that list. I'm going to stick with square root of 2. If we add it, what do we get? There's no way to add square root of 2 to a fraction, so for these, all we're going to do is plug it into the calculator. We're going to see if we get a fraction, a decimal that ends or repeats, or a decimal that never ends or repeats. So we're going to plug it into our calculator. So 2 over 3, you're going to hit alpha y equals, enter to get 2 over 3. Get these out of my way. Then you're going to add square root of 2. So second square root 2. Second x squared, I mean 2. And we get this weird decimal, 2.080880229. So then look at your chart. Is it a fraction? Well, clearly that's a decimal. Is it a decimal that ends? No, it kept going. Now it ends on your calculator, but if it ever gives you a super long decimal like that, it's because your calculator ran out of space to write, but there's actually more decimals after that. Is it a decimal that repeats? Those are the ones that fall under rational. It does repeat for just a second, 0.0808, but after that, it starts doing different numbers. It has to repeat all the way through. So because it doesn't repeat all the way through, it's not rational. So then it's going to fall on the other side. Irrational are your numbers that never end and they never repeat. So it didn't repeat all the way through and it didn't end just because your calculator ran out of space. So because we get this long, crazy decimal, this is going to be irrational. Now we always want to try different numbers for this. You can do, for rational, you could try 0. You could try negative numbers like -7. For irrational, you can try pi, or you can try a really long decimal if you want to. There's no way to type a really long decimal into your calculator without stopping at some point, so I don't recommend that one. I would stick with pi and square root of 2. But no matter what you add together for rational and irrational, it's always going to come out to rational. Irrational. Always irrational. No matter what. Okay, the second example for number 4. Again, I'm not going to watch the video on this. I'm just going to plug in some numbers for rational and irrational. Erase this. So for our irrational numbers, remember we have pi and square roots that we don't know, like 2. For rational, we can use fractions like 2 over 3. We could use regular numbers like 5 or 0. Or you could use a regular decimal like, let's go 2.5. So you could use any of those. Product means multiply. So if we multiply these together, what do we get? So I'm just going to take the first one, 2 over 3 for our rational, and multiply it by the first one over here, pi. Do we get a normal decimal, or do we get a crazy decimal if we plug this in? So 2 over 3, we're going to put alpha y equals 2 over 3, and then times pi. Pi is this little blue button right here below clear. So to get that, we're going to hit second and this little up button right here. It's called a caret or a rooftop button. But hit second and hit that little up button. And then when we hit enter, do we get a normal, like ending decimal or repeating decimal, or do we get a crazy random decimal? Well, none of it repeated all the way through. And again, it doesn't just stop because your calculator runs out of room. It does keep going if it's that long. So because it's that long and nothing repeats, that's an irrational number. Now for this one, I am going to try one more thing that I want to show you. I'm going to go back over to my list for rational, and I'm going to pick 0. For irrational, you can stick with pi, or you can go square root of 2. I'm going to go square root of 2, because I haven't used it, and see what we get for that. Now, if you remember the rule for 0, what do you get anytime you multiply by 0? Everything times 0 should be one single answer. If you don't know, you can plug it in, and we get 0. Is 0 rational or irrational? Well, if we go back to our chart, 0 is right here under integer and whole number, which is on our rational side. So because it's on our rational side, this answer is actually rational. So for one of them we got irrational, for the other we got rational. The thing with product is 0 is always, no matter what you multiply it by, if you want to go through and multiply it by pi, that's completely fine. It's still going to come out to 0 though. It doesn't matter what you multiply it by. It's still 0. Everything else we try on our rational and irrational list, if we multiply it, is all going to give us crazy decimals. So you can go through and try 5. You can try 2.5. And I'll do those for you. That's still going to give us a weird decimal. If you want to try 2.5, and I'll go square root of 2 on this one. Oops, my bad. Times square root of 2. That still gives us a really weird decimal. So it doesn't matter what other numbers you try, it's always going to be irrational. The only exception is 0. So this is always irrational, except with 0. If you use 0, it comes out to rational. If you use anything else, it'll be irrational. Okay, I'm gonna add one more page here. Okay, our try it, which is in your workbook, for example 4, is the difference of a rational number and an irrational always irrational? So this goes back to the sum, like we did on the first example for number 4. We can try different numbers for rational. I'm just going to pick a random fraction. Stick with 2 over 3. That's what I've been using. And for irrational, I'm going to go with pi. If you want to pick a square root, you can do that. But, so if we take the difference means subtract. So if we subtract these, so 2 over 3 minus pi, what do we get? We're going to go over here, grab our calculator, and plug in alpha y equals, enter, do 2 over 3, and minus pi, which is second, and that rooftop button. Do we get a normal, repeating, or ending decimal, or do we get a crazy decimal? Well, in this case, we get a crazy random decimal. No rhyme or reason to it. It's negative, that doesn't matter. And irrational can be negative. But it's going to be a negative, weird decimal that has no pattern to it. So because it's a weird decimal with no pattern, it's going to be irrational. Now we can try it with 0 because we saw in the last one 0 was an exception. So if you want to change that to 0 minus pi or 0 minus square root of 2, or something like that, you're more than welcome to. See if it gives you a normal decimal or if it gives you 0. So I'll try square root of 2. If I subtract that, 0 minus square root of 2, it's still going to give us one of those weird random decimals. So even 0 on this didn't change our answer. It's always going to be irrational. So the sum and difference, it's not how you spell sum, sorry. Sum and difference of an irrational and rational always come out to irrational. The product always comes out to irrational unless, there's an exception, unless you use 0. That in that case, it comes out to rational. So what do you think quotient would be if we tried that? I'm going to let y'all ponder that one. Try quotient and see what you get. Go back to your product example if you're not sure. Okay, next we're going to move on to, oh, we have one more example for example. Try it, not example. So this one's not in your workbook or your book. This is just an additional one to give you a little bit of extra practice to make sure we remember what we're doing. So for this, we're going to order our numbers from least to greatest, just like we were doing a second ago, except this time they're all square roots. So just like we did before, we're going to put these into our calculator. So I'm going to move this over here so we can see. So to get your square root symbol, you're going to hit second square root, x squared right here. To get your fraction, 9/7, remember we don't want a fraction, we want a decimal. So you don't have to put it in as a fraction. You can just put 9 divided by 7 because we want to compare the decimals. So I'm going to round that off to 1.13. Then we have square root of 8. So second x squared to get your square root, and then 8, that's 2.83. And the last one, second x squared to get your square root, 54/7. 54 divided by 7. And that one gives us 2.78 if we round it correctly. So which one is the least? $1.13, $2.83, or $2.78? Well, clearly $1 is less than $2, so that square root of 9/7 is going first. And then which one's less between these? Well, 278 is less than 283, so it's going to be square root of 54/7, and then your 283 square root of 8 will be last. And we can check our solution to make sure. So we have square root of 9/7, square root of 54/7, and square root of 8. And we got it perfect. Okay, so now we're going to move on to our concept summary. This is just a little review of everything that we've done talking about rational and irrational. I talked about this a little bit at the end of example 4 with these. If you add two rational numbers, remember those are your fractions, like 2/3 plus 6/7. Because it's an integer on the top and the bottom, it's always going to stay an integer. So an integer plus integer, a rational plus a rational, always stays rational. When you multiply them, that's what product is, multiplication. Sum is addition. When you multiply two rationals, they're always going to stay rational. Pencils times pencils is pencils. It only changes when we have a rational and an irrational. If we add a rational and irrational, like 2/3 plus pi, that's always going to come out to one of those really long decimals. Those are always irrational. If we take the product and multiply it of a non-zero rational number, remember 0 had an exception on it, but if it's not 0 and we take 2/3 times pi, it's always going to be irrational. Just remember 0 was the exception there. for 0, it came out to be rational. And then they plugged in numbers to give you more examples down here. So you can look at those. Okay, next on our list, we're not going to do the do you understand because that's more of a classroom discussion type question. And because we don't have a classroom to do a discussion on this, we're going to skip those. You're more than welcome to read through them and see what you think, but we don't have a class to discuss it. So we're going to move down to the do you know how. This is going to be numbers 6 through 10 in your textbook, so you can look through those. And it's also in your workbook, so you can do your work and write it down. So back to the very first example we did. That's what this one's about. Determine whether set B is a subset of A. So A has 0, 1, 2, 3, 4, and B has 1 and 2. So could it be a subset of A? Remember subsets on our original question, in set A we had 1 through 10, and in set B we had the evens from that number. So B was just a subset of the even numbers. Could A be a subset, meaning they have something in common with B? Sorry, is B a subset of A? Does B have anything in common with A? Well, we have 1 in both of them, and we have 2 in both of them. Because they have all of the numbers in common in B with some of them in A, it is a subset. It doesn't have to have everything in common, but it's got to have something in common. All of your numbers in B have to be inside of A. So yes, B is a subset of A because all of B is inside of A. Okay, is B a subset of A here? So A has 2, 3, 5, 7, 11, and B has 3, 5, 7, 9, 11. Again, for B to be a subset, all of your numbers in B have to be inside of A. Just like our very first example that we had at the beginning of this video, where A was the numbers 1 through 10, and B was just the even of that set. It was just 2, 4, 6, 8, and 10. 2, 4, 6, 8, and 10 were within 1 through 10. It just didn't cover every single number. But all of these numbers are inside of A. Are all of these numbers inside of A? Is 3 there? Yes. Is 5 there? Yes. Is 7? Yes. Is 9? No. Because 9 is different, B cannot be a subset. It has to be the same. So no, B is not a subset of A. Number 8, ordering least to greatest. Again, you just want to check these with your decimals. That's going to be the easiest way to go about this. So if we check our decimals, we want to do square root of 200. So second x squared gives you square root and then 200. So we can round this off to 14.14. Our second one's already 14. We don't have to change that. But on our last one, let's do 14 divided by 3 to change that to a decimal. So 4.6 repeating. I'm just going to change it to 4.67 because we just need to compare a couple decimal places. We don't have to compare the whole thing. So what's the least? $14.14, $14, or $4.67. Clearly 4 is a lot less than 14. So we're going to get 4.67, which is your 14 over 3. I'm going to write it out here so we know what we're doing. So 14 over 3. And then what's less, 14 and 14 cents or just 14? Well, 14 is less. And then you got your square root of 200 with the $14.14. So we'll write that in our answer. 14 and 14.14. And we can check it. We put 14 over 3 first for that decimal, 14 in the middle, and square root of 200 was that decimal at the end. Perfect. Okay, number 9. Again, let's change these to decimals. Just put them in your calculator. So 2 divided by 3 to change it to a decimal is going to be 0.67 if you round it off. Square root of 9 over 16. Again, we don't need to put it in as a fraction because we just want to get that decimal. So 9 divided by 16 in the square root. So 0.75. And then 0.6 is already out here. To give it 2 decimal places to match the rest, I'm just going to add a 0 to the end. So what is the least? 67 cents, 75 cents, or 60 cents? Well, 60 cents is less than the rest. And then your 0.67, which is 2 over 3. And then your 0.75 cents, which is square root of 9 over 16. And we can type it in our blank. So our 0.67, sorry, 0.6, then our 0.67, then 0.75. Exactly what we put. 0.6 is first, 2 over 3, and then square root of 9 over 16. Last one, we have a park here shown is in the shape of a square. A square just means all of your sides are going to be the same. So whatever you get for one side, that's going to be the answer for all 4 of them. Is the perimeter shown rational or irrational? So, because all 4 of our sides are the same, I'm going to call all of them side. We have 4 sides. So, side plus side plus side plus side. And then all of that equals your area here. Oh, this is area. Sorry, it's asking for perimeter. Okay, it's asking for perimeter, but this is your area. For perimeter, you add everything up. But for area, we multiply length times width. So this is your length, this is your width. So side times side gives us side squared. So in this case, for our area formula, area equals length times width. We just found out length times width is s squared. Our area, let me write this the other way so I have my room. Our area is up here. That's 24,200. That equals your length times width, which we said down here was s squared. Now to find just what one side is, to get rid of this squared, the opposite of squared is going to be square root. So you square what you do to one side, you have to do the other, so you have to square root the other side. It'll cancel out your squareds here, and then you just square root this side. So let me move this. So square root of 24,200. Well, that gives us one of those really long decimals. Not repeating, not ending. Just because your calculator ends, it doesn't end. So because it's one of those really long decimals, those are your irrational decimals. So each side here is going to be irrational. So if we take an irrational plus an irrational plus an irrational plus an irrational, it's the same exact concept as when we were doing the sum of rational plus rational. If you take a pencil plus a pencil, what do you get? Well, you get a pencil. So if you take irrational plus irrational plus irrational plus irrational, doesn't matter how many times you add it, if you take the same thing and add it up, what do you get? You're going to get an irrational number. It's not magically going to change to rational if they're all the same. So because we had to square root that number and get a really long decimal, one of those irrational decimals, your answer is always going to stay irrational. Yep, your perimeter is irrational. Okay, so go through your practice. Y'all have been assigned practice on the textbook. If you look into your Pearson account, you can see your assignments there. Go through your practice, do those, and submit those. And if you have any questions, you can always ask your teacher. You can email them or message them through Schoology. Good luck.